may have something to do with, you're changing from relatively coarse to a relatively fine sediment, so it's going to change the dispersal patterns. But in any case, I mean, we're having a major effect in the coastal ocean in this particular example, and you can see that human signature prominently in the sediment record and in the sediment budget.
So how did you know the historic input, or the prehistoric?
That's a little more difficult to get to, so that's a great question. We don't have river aging estimates, back that far, obviously. And so a lot of these were estimates based on the Ketterer model. One of the things they looked at is lake records. So they looked at varving in some of the lakes in nearby catchments and looked at the shift in terms of the thickness of some of the banding to figure out what the paleo discharge was relative to the modern discharge. So I guess the answer is it's scaled to the lake records. That's probably our biggest, but you're right on point with the question because that's one of the bigger uncertainties. So I guess to recap the New Zealand results before I transition into Alaska. I mean, we've got this wonderful signature in the textual record of transgression, regression. We see ENSO, increased storminess probably, and this humongous signature of fine sediment from humans. Maybe a human fertilization event and a sense that we may be changing the mass fluxes in the shelf from capture to bypassing.
Hey guys,
Yeah, sure.
Before you go to Alaska.
Yep.
You should be going to Alaska. Huh?
Yes, I'm going to Alaska.
What about the coastal system? Did the coastal system change significantly? The coastal morphology, the progradation of the spits? How about the rivers? Did it change from a braided to a meandering or vice versa?
The rivers in they have levee guides now in the lower Waipoua River. You can see one of the things that you see actually. The river's been. It hasn't been paved over like the Mississippi. They do have some river guides. One of the big changes that you see in the catchment because of the increased sediment loading is huge rates of aggradation in the floodplain. It just, starting about 100 years ago, I mean, the floodplain is just zooming up. And so, you see it in I mean, that's one of the big signatures that you see.
Is that part of the missing 70% or?
No, I don't think so. But that hits on another sore. It's always a sore subject in terms of, what is missing between the river gauging station and the mouth, and so, I haven't done that calculation, but my guess is that may account for a small fraction, but probably not the six-fold increase that we're seeing. Okay, so going to shift gears now and take you, and this is kind of more of a more tourish rather than science-ish, but and this is some work that we've been doing recently, funded by NSF, a RAPID program. If you look at the sediment yields from North America, I mean, you see a couple of big arrows, and one is, of course, the Mississippi River and the Gulf of Mexico. And the other one is up here in Alaska. And again, this is an active margin where high rainfall, high uplift, erodible rocks lead to very high sediment yields. And so we had an opportunity to, which I'll describe in a moment, to look at the Copper River this past summer. So this is just to give you a little background on the copper. So this is Alaska, Gulf of Alaska, this is our study area, and then this is a blow-up showing the drainage basin for the Copper River. So Copper River is the major sediment supplier to the Gulf of Alaska two mountain ranges, which I'll come back later, I'll mention them again. I just lost my pointer, that's okay. So the Wrangell Mountains to the north, and the Chugach Mountains to the south. And then just Prince William Sound is over to the west, so just to kind of, I'll come back to these, but the main point I want to make now is that these mountain ranges are part of accretionary terrains in this collision margin. They have very different rock compositions and different chemical different elemental compositions. So where does the copper sit in terms of sort of its size and discharge relative to some common comparisons? Okay, so the Mississippi is obviously one of the big references for us. I mean, it's got a fairly big drainage basin. You know, the elevations range up pretty high in the Rockies. And, you know, the overall sediment discharge in megatons per year is fairly high, but the yield is not so high relative to the copper. So the Copper River, which has a much smaller drainage basin, higher elevations, moderate discharge, high runoff, and high yield. So if you look at the sediment yield, again, sort of a measure of how much sediment is coming off per unit area per time in these mountainous collision margins, it's phenomenal. Okay, so how did I get to go to Alaska? This is what brought us there. It was literally this amazing event back in January, in the week of January 18th of 2012. They had 6.1 meters of snowfall reported in Cordova. You know, we just heard about this recent little flurry that they had up north, you know, which was about 3 feet. People were kind of excited about it. Well, 6.1 meters in this area. And this is a place that's used to a lot of snowfall. So we felt that was, oh, and here's sort of, if you go back you can go back to 1950 and look at the integrated snowfall from December to February. And what happened in 2012 is like nothing we'd ever seen before. So we used this as an in to ask for a little bit of money from NSF, just because we felt like with such a high snowfall event during the winter, we had the opportunity to monitor a potentially historic spring melt of the Copper River. And so they bid, and they threw us a couple of dollars, and we were able to get up there to look at this. And I just want to tell you a little bit about what we found. So here again is the snowpack this is from April, way above normal. And one of the things, in addition to wanting to look at the outflow of the copper and the sediment dispersal from the copper into the Gulf of Alaska during the spring melt, we are also kind of interested in tracing where this material is ending up. So this is the mouth of the Copper River. This is actually from 2011, but what it shows is the typical situation where the currents in the Gulf of Alaska sweep the sediment plume towards the west, and this plume actually enters, and you can kind of see it here. It's a bit faint. It actually enters into Prince William Sound. And we have pretty good evidence that Prince William Sound, which was a deeply scoured fjord after the last glaciation, contains a pretty thick Holocene sequence. So remember on the Waiapoas Shelf, we were looking at something like a 75 meter or so thick at maximum. Here in Prince William Sound, you've got something like 150 meters of Holocene, and it's just horizontally bedded. I mean, so in terms of looking for a place where we might extract a record of past climate, we felt like this was a good place to look, so we were poking around up there. So just a couple of things that we were able to do during our trip up there. This is the road out from Cordova towards the Copper River was we still had a bit of snow on the ground. But you can see, I mean, this river is pretty turbid, and I just want to give you a sense of what it felt like. We came out to the bridge on the way to we tried to get up to the gauging station, which is where the $1 Million Bridge, which was pretty far up the basin. And we came to this particular bridge before that, and it was washed out. The river had scoured through the far end, and so we couldn't take the car across. But we wanted to get some suspended sediment samples. And it's hard to see in the picture, but I think that, just to kind of give you a sense of what this river is like in its full fury during the spring melt. I mean, it was ripping. We're out on this bridge.
Oh, man, I can feel the bridge moving.
And you can literally, and the bridge is kind of going back and forth. And here's my colleague and former student, Tim Dillon, kind of trying to get a water sample off the bridge. You can see out here the sample bottle is just speeding away.
I think it's going.
So, needless to say, we survived the experience, but it was pretty awesome to see the full fury of the Copper River. So we actually had a very successful sampling trip using local vessels. I mean, we had a small sort of converted trawler that we used to collect a series of gravity cores in Prince William Sound, and then along with the Prince William Sound Science Center, they have a 17-meter, I think it's 17-meter aluminum research vessel that we were able to get out, and we were doing some water column work as well as seabed sampling off of the Copper River, right off the mouth. So, when we planned this short trip, because we didn't have a lot of money, we just had to sort of guess as to, when is the flood going to come? When's the spring melt going to happen? And you never know. The hydrograph for the copper varies from year to year, depending on the climatic conditions and how much snowfall there's been and how fast summer cranks up. But we guessed late June. These red bars are actually when we were out sampling, and the overall line is the hydrograph. So this is the spring melt peak, and we hit it pretty close. So we were out in Prince William Sound at this point, and then just after the peak, we were out off the Copper River. There's another later peak, and then actually this past year there was one in October. I'm not really sure yet what caused that. It could have been a eucalyptus, which is an outburst event in the Copper River Basin, or maybe another odd sort of warm period, which caused that peak. But in any case, we hit the spring peak. This MODIS image actually was collected from when we were out there, so you can see the river. So we had good luck in timing. We also had good luck in weather, because going out in the Gulf of Alaska in a small aluminum boat is a dicey proposition. And so you can see the conditions that we were out were pretty favorable. And we certainly saw the plume coming out of the river. This is from 10 or so kilometers offshore, looking towards the Copper River Basin, and you can see you can put your finger on the front here from the river coming out. So just a couple words about one of the things we were trying to accomplish at the mouth of the Copper. We attempted to use another tracer, cosmogenic beryllium-7, which has a very short half-life. It's formed in the atmosphere, comes out in wet and dry precipitation, it's particle reactive. And in the last 10 years or so, it's been used as a tracer of river input. A lot of it is locked in the catchment. Studies off the Eel River in California, the New Zealand rivers that I talked about earlier, and the Po River have all shown this great relationship between river input having a nice high beryllium signature. So you can look at and trace this water coming out. But the idea was we'd be able to trace the Copper River suspended sediment plume over into Prince William Sound using this beryllium-7 tracer and get some idea how fast it was moving around. Well, sometimes in science, you don't get exactly what you expect. And so when we measured beryllium off the mouth of the copper, there was nothing there during this major flooding event. And so we learned something new, which is that the paradigm of beryllium-7 being a tracer of river input is not always true. And in this case, we think it relates to the fact that most of the water coming out in this first pulse from the spring melt was from snowpack that had been sitting around since January. And so most of the beryllium-7 with its very short half-life had decayed to nothing. And so the rivers coming out were depauperate beryllium. So that was kind of a wash. The coring that we did in Prince William Sound was a little more productive. And I want to talk about, I'll show you some data from two core sites that we've looked at. One is right at the mouth of Hinchinbrook entrance here, P7, where the plume of the Copper River enters into Prince William Sound, and the other one in the north part of Prince William Sound, near to the Columbia Glacier. I do have to digress, and this is kind of just tell you that this, we were sampling from this converted trawler, and this is really old school stuff. We had a bucket of line, so about 1,600. The water depths that were gravity coring in Prince William Sound are approaching 500 meters. So this is not shallow water shelf sampling. We had a crab pot winch, and so the tension on the line is all being applied by two plates, which are squeezed together. So the friction is holding the line in. And the surprised look on my graduate student's face is had been just after the rope came off that crab pot winch and the core free fell 500 meters to the bottom. We got a perfect core. But you should have seen the people running away from that bucket of rope. Okay. So the cores actually had some very nice records. We looked at the two cores, the one at the mouth of Hinchinbrook and the one up towards the north of the Columbia Glacier, and we did our normal geochronology dance. We measured the lead-210 activity, and this is almost 150 centimeter core. We've got excess lead-210 down at the base. You can get, if you draw a regression line through that, you get accumulation rates of about 6 centimeters per year. So that stuff is just piling up at the mouth of Hinchinbrook entrance. This is the cesium-137 profile. You can see we see cesium-137 throughout. So all that stuff had been deposited after 1950. If you look at the core X-radiograph itself, it looks varved. It's just layer by layer by layer. And so there's no bioturbation or disturbance of the signal within this core. Up to the north, near Columbia Glacier, you can see what we think is a turbidite layer in the X-ray radiograph. So that light layer is a sand layer. It's hard to see it here, but it's scoured at the base. Turns out that if you look at the cesium profile, the peak in the cesium profile is right here. The turbidite is right there. Now the turbidite, the activity in the turbidite is low because it's sand, and so there's not much radioactivity associated with the sand because it's got a low surface area. But the fact that those peaks are so close suggests to us that turbidite may have resulted from the Great Alaskan Earthquake in 1964, because that's the peak of the cesium. And for those of you who don't know, the Great Alaskan Earthquake, magnitude 9.2 in the moment scale, was the second greatest earthquake recorded in history. I mean, it just rocked the place. And this is actually a picture of Anchorage, I think, which is way away from the epicenter, which was in the north part of Prince William Sound. So here's the epicenter. right over top of Prince William Sound. So, again, one of the main thing that we were trying to figure out here is if, you know, do we have the opportunity to kind of develop a high-resolution climate record based on what's happening in this particular, it's kind of a unique environment. I mean, you've got the Copper River, there are different discharging from different catchments in terms of the mineralogy. And so we thought we just take a look at the elemental composition, downcore elemental composition, and you know, they've got this great gizmo up at the IODP facility in College Station. You can zap your core through it and look at elements from, you know, silicon up to uranium at pretty high resolution. So we scanned a couple of these cores at about half centimeter resolution just to kind of see what we could pull out. And this shows silicon aluminum ratios. And you can see there's a pretty nice, and this is depth in the core in millimeters, you can see a pretty nice periodicity. A couple of big spikes here. We think that the large spikes are because of silicon-rich tephras, which are deposited from a few historic eruptions to the north. And we also looked at this, we kind of looked at the signal. This is actually a different ratio. We looked at zinc to sulfur, which showed a really nice periodicity. And because we had the lead-210 accumulation rates, we know the timing, and we just ran a simple fast Fourier transform to look at the dominant frequencies within these and so what we ended up with is a really nice annual signal. And so we're thinking at this point that the Copper River annual discharge hydrograph is recorded within Prince William Sound, and that the zinc sulfur, in this case, the high zinc is recording inputs from the northern Prince William Sound area where there's a series of sulfide deposits, and the valleys or the low points are the Copper River signature. So the variation between Copper River and local inputs is creating this periodicity. So we're pretty excited by this. The other thing that we looked at, the more we look at this, the more that it appears that we've really kind of got we've hit a gold mine in a sense. So we looked at strontium and manganese, and this is from the Hinchinbrook core at the mouth